Okay, come on guys, please, can we move over?
Yeah.
What's kicking off already? Okay. Okay, Piotr, I'll hand it over to you.
Hello? Okay. So another topic today will be a topic from our Elasticon tour. So it's called Scale with Confidence. So this is the whole story how you start from your laptop and move to 100 nodes or beyond even. So there is a lot of documentation available. Probably many of you already saw how many different things you can tweak in Elasticsearch to actually get it running in performant way. But we obviously don't have too much time today, so we'll try to shrink it to really probably even below 30 minutes. So it will be, as we calculated, around 2 seconds per page, so not much. So I'll start first from what we do first when we move from one single node, when you already tried your installation, everything works well on your laptop, but then you would like to actually run it in production. And what's next step? So we start from 3 nodes. So not sure how many of you know that 3 nodes are necessary to run Elastic, and why? Can you raise hands? And why is not 2? Okay, so some of you. Okay, so 3 nodes is because we need to ensure quorum. So what means quorum? Quorum is the way how we elect master nodes. So imagine that you have 2 nodes, and which node will know when we actually split connection between those 2? How we know that which one should be master? Which data should be considered to be valid when we have split networks? We don't know. So the whole concept actually was created in Roman Empire when they got really big lands covered, and quite often they've been divided and separated from themselves, and they needed to find a way how to vote and how to actually run their empire in a consistent way without waiting for other guys to come, because actually they couldn't. So they established quorum rule, which means that the majority actually wins. So that's why to have majority, we need to have at least 3 nodes. So that's why 3 nodes makes sure that we will not end up with a split brain problem. That means that we'll have 2 versions and we don't know which is true version which should be used. So that's the number 3, really important. Everybody should remember, never, never, ever 2 nodes, because that will be disaster in production system. So when we actually start from 3 nodes, we'll have something which is called omni nodes. Omni nodes will have all the functions on one single node. And what are these functions? So we have data nodes, which store data and actually do search and process all the data. We have master nodes, which coordinate, keep the cluster state information. We have coordinating nodes, which are doing the aggregations for the searches. They help with the bulk indexing and so on, and coordinate queries to the nodes. We have ingest nodes, ingest type, which is helping to pre-process data. So we have special processors which can transform data and execute similar tasks to Logstash currently. So they are still very limited in comparison to Logstash, but a number of different features in processes is still growing, and we'll try to make it more usable and useful just in Elasticsearch, so the scalability will be much easier with ingest nodes than Logstash. So when you actually start building production cluster, it is important to look at few very big things from my perspective. So one of those things will be actually how you treat your data. Actually, what happens when you put data to your cluster, and how you create models for the data. So as you may know, we say that in Elastic you can put any type of data, but we also say that we have a schema on write. So that means that actually data has to have its own format, and we need to define how this data should be written. So it's really important to look at Elastic setting, which is called dynamic. Dynamic will create mapping on the fly. When we push new fields, new data, these fields will be created automatically, and our mapping will expand for the new data. So that's very good when we would like to check how our data looks like, but it's really bad idea to keep this setting set to true, because we may end up with out of memory, because when we have some, for example, error, that cardinality of the field naming will be really high, then will grow to hundreds of columns, and as you know, columns are not without the cost. So every time we add a new column, new processing has to be applied for this column, and this will take memory. So we can change this setting to false. That means that we'll still accept documents and documents which will have new fields which are not yet in the mapping, that will be just discarded, but there will be no exception. And the last, so that can be used in production. And the last one, which is probably when your system is getting the most, is becoming the most mature, it will be probably a good idea to set it to strict. So now I'll move to sharding. So I would try to describe to you how Elastic looks inside. So Elasticsearch uses Lucene indexes. So what Philip explained on the beginning. So Elastic is built on top of the Lucene, and shard is actually a Lucene instance. So it's self-contained processing with the data together with us. So shards can move around nodes. We can make some configurations which will move data from, for example, nodes dedicated to for fast indexing and fast search, to nodes when this data is no longer important like it was in the beginning, like later, maybe like older data can be moved to the slower nodes, which will be much more efficient in storing the data. So those are shards. So shards are consisting from segments. So when segments, actually how segments are created. So whenever you put new data to Elasticsearch, this new data is going to buffer. Then there is a refresh process which will write this data to Elasticsearch, and at that time new segment will be created. And what are really segments? Segments are files on file system. So the more segments you have, the more files are open, and obviously this is going to be less efficient. So shards are using CPU and RAM, and segments are using CPU, RAM, and also file handlers. So the more of this actually makes Elasticsearch to work harder. So how many shards should we have in our installation? So we usually say, well, it depends, because it depends on many factors. So as you may think, Elasticsearch is a platform which starts by default as the standard family car, if you compare that to cars, and you can tweak it to be Ferrari or big truck. So, and number of shards and how shards are configured actually, those defines how Elastic will be working and how effectively will be applicable to your particular use case. So we should keep in mind that we should have no more than 25 shards per 1 GB of RAM. So when looking at that, typical node which we consider to be best performant node at the moment is 64 GB of RAM. So this is around 700 shards on this particular node. And if we exceed this number, we see customers who are having, for example, thousands, or even I saw a customer who had 20,000 shards, and they were complaining that the performance for Elastic is not very good. It was collapsing, it was actually couldn't synchronize, and they have many problems. So, and then problem two, actually it was very easy to fix the problem. They shrink the indices and shards, and they got many less shards, and they fixed their problem. So remember, 25 shards per gigabyte is probably maximum you should use. And how big shards should be. So now it's again which direction you'd like to go. If you'd like to go for more storage and slower responses, then you'll be probably targeting something between 10 and 50 gigabytes per shard. If you like to be fast in search, like Wikipedia, search as you type, probably you will go to something between 1 and 10 gigabytes per shard. And then one quick note that default setting for version 6, still version 6, was 5 shards for index, and now it will be 1. So when somebody is not actually having that in the mapping, then you should be careful when new indexes are created, because that will be changed. So what kind of operations can be applied to fix your problems, actually to maybe adjust platforms? So we can merge segments inside the shards to make it more efficient, so actually to release file handlers and so on by force merge. So we need to remember this kind of operation should be done on the index which is no longer readable. So when we actually have indexes, for example, written daily, that should be on the index which is already, let's say, read-only. So no new segments will be created. So shards can be shrunk. So we can combine few shards when shards are small, and actually they are still below the limits. When we put maybe not enough data daily, and we create daily indices, so we can use shrink methods to actually make less shards, and again avoid problem of having too many shards. On the other way, actually, when you push too much data to the shards and they are slow, then you can split them. And then the last interesting approach is actually to reindex data. When you actually maybe define index with not enough shards, and then you figure out that you need to add more nodes and you like to add more processing, then probably reindexing will be only choice in that way. So then what we do to move to more nodes, actually to make our system more, yeah?
So one quick question. So on the previous slide, it said that it's like awesome. Does it mean that there is something like ongoing process?
Yeah, so merging is happening all the time. It's scheduled. So there is, I will find the link actually, but there is a blog entry on Elastic with videos how merging is working in the time. So they are constantly merged, but we may end up actually with still not fully merged segments. Okay, moving to more than 3 nodes, 10 nodes and beyond. When we have more nodes, actually we can figure out that pressure put on the CPU and memory is that high that master nodes actually cannot do their job well. So then we have problems really with master election, with synchronizing state for Elasticsearch. So we need to, the first task will be to take out master nodes. Master nodes, obviously, they don't need to be as big as data nodes for storing data, so there are different requirements. And then we can think about taking out coordinating nodes and machine learning nodes. Machine learning nodes, when you have the more jobs are defined, the more CPU load is taken, and then obviously it will also impact searches. So when we make this kind of segregation for the roles, then whole cluster will work much more efficient. So then very useful, there are very useful operations which can help you actually to control how your indices and data is stored in Elastic. So we have rollover function which can create new indices. So it's exactly the same like you have log rotation in syslog, for example. You can create new indices, and then you can create aliases, so you always query, for example, the last one or index to the last index. And then what happens when we need to go to even more nodes, because our data is big, we are reaching, let's say, hundreds of terabytes or petabytes of data. We need to think how to scale it out even more. So we have ingest nodes, we have hot nodes, and warm nodes. So this is a concept where we create a node tier where we have very fast storage. So for example, that will be on SSD drives. And we actually put less data on that, so to be able to quickly index and query this data. And then the second layer of nodes will be warm nodes, which may have spinning disks, much more space. So they will be a little bit slower, but they are not queried so frequently. And actually, one thing which is missing here, and I will just mention to you, is already available in the documentation, is something which is called frozen indices. So you can do frozen or cold nodes, let's call it cold nodes, which can go even beyond what's possible in warm nodes, so we can store way more data. And what would be the difference? So the data which in the warm nodes is still in the memory. In the frozen indices, that data will be offloaded to the disk and only loaded back to the memory when the query will come. So then we query data, we send the query, data is loaded to the memory, and then is taken out from the memory, memory is released, and then in that way we actually optimize usage of memory on our nodes, and then we can have much bigger data sets stored on Elastic. So that will be coming in next releases, it will be updated so we can read documentation. So then, as exactly like we did before, we have machine learning nodes, coordinating nodes, and alerting. Alerting, actually, those are the nodes where we have an index, watcher index, which describes what kind of searches are executed. So when you actually create this kind of index only on one type of node, because there is no type actually alerting node. You need to actually create that by having configuration or index responsible for creating for configuring watcher on this particular node, and you can do that basically configuring the how the indexes will be routed to the nodes. And then there is last thing I would like to talk about is how we can influence the storage and how much data can be stored. So we have multiple different parameters we can turn off, turn on. So actually, when you look at the mapping, in mapping, first of all, we define what type of fields we have. If those fields will be text fields, or those fields will be keywords. So when we actually, by default, everything is keyword and text. That means that we use two different things. We index them, so we create inverse index, and we create all the data structures required for aggregations and time series data. So when we create mapping, so for example, logging use cases where we look for things, usually they don't require these particular data structures like text and keywords for all the fields. So only selected fields will be searchable as full text search, but IP address, for example, doesn't need to be searchable. The same for node name and many other things. So when you actually configure, just pay attention how you configure mappings. So you can control all these things in the mappings. You can turn off inverse indexing. You can turn off source when you don't need sources. You just need to look for the records, but you don't need to retrieve data actually correlated with that. Or you don't need to reindex this data, or you don't think it will be useful, but you need to find a particular records, then source is not required. Doc values can be disabled. Store is actually something which is similar to source, but and this is by default disabled. And then we have metadata. So there is quick calculation, and you see how this is impacting the space on the drive. Obviously, there are a few more optimizations, like you can change the compression ratio. Best compression will work a little bit slower, but also you can achieve from 15 to 25% lower the disk space used by the indexes. So we have, I don't know, Ken, if we'll be sharing the slides to the audience who register. Probably that's a good idea, because we have some links here, some descriptions, so then you can look after that when you actually get this content. You'll have links here to few interesting topics. So we created a tool for benchmarking, which is called Rally. So you can download this tool, run queries against your clusters, and you can actually see what will be the response. So this is how it looks. It will produce all the stats from your cluster, and you'll be able to judge how you configured your cluster. Then there are detailed descriptions for all these things which I mentioned, so how to do mappings, how to do different operations like lowers, rollovers, shrink, split operations, and then also a little bit about search, how to profile search, and how to optimize it. And this is very interesting link. Here, hold my beer customer stories to learn from, as told by support. So there is a video on how Elastic works internally, how data is indexed to Elastic, how queries are performed, how they are actually queued in the Elasticsearch, so you understand a little bit more. Also, guys are describing what kind of bootstrap checks has to be executed initially on the beginning before you run your Elasticsearch cluster in production. And you'll also find a little bit, a few stories from our conferences, for example, how Uber is doing that, or other things. And I think that will be all from scaling, and we move on to Philip now, right?
Do we need to change computer? Yeah, okay. So while you just change computer. Yeah, guys, so we will, of course, we'll share the slides, and we'll come back to you on how we're going to share those slides afterwards. And also, guys, as I said, we're building an Elastic ecosystem here. So very much want to hear your feedback. You can contact us on our Facebook page or on LinkedIn. What was good, what was bad, for future events, what would you like to see, whether maybe it's workshops or whether it's whatever topics you want to cover. And we'll do our best. We're working with Elastic to try and organize these events as the year goes on. So the more feedback we get, guys, the more we'll do. So looking forward to that. We're always looking for good people here as well as we build out, scale out the Elastic teams. So if you are interested in working on different various Elastic projects, then please do reach out to our HR team. And that's about it. Okay, Philip, are we good to go?
Cool. So, let's try to do something a bit more hands-on. Logging. Who's already using some centralized logging? Okay, that's far too few. Oftentimes you probably start developing with something like you see logs scrolling by and everything is fine, and then you continue, and then at some point you just output your logs, and then maybe you start using tailf to see what is going on. Who's using tailf to see their logs? Okay, brave that you're admitting that. And maybe at some point you use less plus f. Anybody knows what the advantage of less plus f over tailf is? You can just break out of that and then search in it, and then you can keep tailing, whereas in tailf you always need to get out of the program to start searching. And less plus f is slightly nicer, but it's still not so great. And oftentimes you're then saying, oh, this is all fine, and it works. And then you put everything to production. And in production, you start having 3 windows. For example, you have 3 services or 3 servers where you run stuff. And this is okay, and then you scale it up, and then you have probably like 5 or 10 or whatever windows. And at some point, you don't really know where your stuff is happening anymore. Well, you're sitting in the middle, and then nothing is fine anymore. That is pretty much the point or part we want to avoid. So let's see how we can centralize our logs. So we basically want to log and combine all the things. That's the general idea that we have here. So Paul mentioned already the elk. That's another way to put it. You see Elasticsearch log /Kibana. That's the good old elk that we had. Then we added beats to it, which we call elk-bee or belk. We tried to come up with this logo. You can see it's a bee and it has the elk horn, so it's kind of the combination. The problem is we're always, what Piotr told you, is we're always about scaling. And this is not very scalable. Because what happens if we add another open source thing and we get another letter? Then we probably need to make up another animal, and whatever that letter will be pretty hard to make up another animal. And also we need to redo the entire branding again. So we kind of got rid of that. We just now call it the Elastic Stack because that's very scalable. Whatever open source products we have, we just stick that into that. And we just draw some other colored box around here, and we're good to continue with the branding. Anyway, so what we have in the stack pretty much is, and it might be slightly hard to reach, but here we have, or let's start here. We have beats, which is like a lightweight agent shipper, which can collect information. And that can either forward the data to Elasticsearch directly, or it can forward it to Logstash, which can do parsing and enrichment, put it to Elasticsearch, and then in Kibana we can visualize it. By the way, what do I mean when I say enrichment? Any guesses what could be enrichment in terms of logs? For example, when I have an IP address and I want to get the geo-IP information for that, I want to see like, okay, maybe the country is Poland, or I want to get a geo-point so I can draw it out, that would be enrichment. And we're pretty heavy on the enrichment when we collect the data. So to make search and displaying it afterwards faster, we will do most of the enrichment, or pretty much all of the enrichment up front. So we will always enrich whenever we collect the data, and then store all of that information to make the display and search afterwards faster. Yes, so we will use like a Hello World application to see how logging works here. Let's see where we can do this. I will use just Java, but it works pretty much for anything else. There are no excuses. Even PHP has proper log appenders nowadays. So everybody can do proper logging. There are no excuses for that anymore. So the first thing you probably do is you parse. Like you have a classical log file and then you try to parse that. Who is doing that? Okay, few. Okay, so let's make this a bit more practical. Let's head over to some code. Preferences. Let me quickly make it a bit larger because probably nobody can read that. Oh, that's maybe. Is that kind of readable? I have a super simple program that runs in a loop. So 20 iterations, we have a trace statement for every run, and afterwards we have this pattern where if something is divisible by the count by 15, something happens by 5 and by 3. What pattern is that? Fizz-buzz, where it's either fizz or buzz, but my output is not fizz-buzz, I'm just outputting something else. But basically, we have a trace statement here, then we do something else. So in total, how many log events should we get out of this? Who is for 20? Who is for 40? Who is for more? Hopefully it's 40, because we have a loop with 20 iterations, and then we have the trace statement and we have the other statement. So if I run that, you will get 40 lines of log output, and it's not super spectacular, but it will be enough to see what's happening here. So you can see we have log lines, we have log levels, we have a stack trace, we even do emojis, because we nowadays support emojis everywhere in our stack. So we have all the important features. So what we get is we have a logs folder, and basically we have a log file where all of that information is in. So what you basically do is your basic structure of how to collect that will look something like this. You have a log file, you have the so-called file beat, which is like tail F. It's just tailing the file and collecting the log lines. It's forwarding that to Logstash. Logstash is parsing the lines. So it's basically extracting what is the log level, what is the timestamp, etc. And we put that in Elasticsearch, and then we can visualize it with Kibana. That's kind of the classic log approach that everybody can be doing. And since we have been running that in the background, we've already collected that. So if I head over here, and let's head to the parse index, and you can see we have collected some log events, and you can see, for example, here we have an info event, we have a log message, and we have some other stuff. So that we have collected from that log file. So how did we get that nicely parsed out information? You can see log level, log method, the package, the loop count. How did we parse that out of the message? How do we do that with Logstash? How are we actually parsing? Yes, we're using a regular expression. We call it grok, which is like a named regular expression. What grok is basically doing is you get a regular expression to parse that. And to make it quick, let me just copy 2 lines here and we try it out. So to actually try out how the parsing works, we have something under the development tools which we call the grok debugger. And that is actually very helpful if you want to figure out what is the right regular expression to parse your log lines. So I will add my sample data, which is 2 lines here, and then I think I've copied one part of my potential regular expression already. which looks like this. So here you can see we have a square bracket. Basically, I have it starts. Then we escape the square bracket, and this is one grok pattern that we have here. So what we have is we have first timestamp underscore ISO 8601. That is like the named regular expression, and we put that result into a field called add timestamp. So we have colon and then the field where we put this in. And if I run this here, then we see we have another square bracket, we have the space, and then we extract the log level. If we simulate that, you can see we extract like the right parts from that original log message. So you can see here we had the debug message, and we were extracting that. If you want to see like all the predefined grok patterns that we have, it's in our GitHub account, and basically what you will see here is basically you have all the named regular expressions. So instead of writing the actual regular expression, you can just refer to the name, and that will do the parsing for you. And with the grok debugger, you can just try it out on your log lines and then completely parse it. And that is what we have done now through Logstash, and we have parsed everything correctly, and it works. And you can find the final regular expression in the code. I'll link to the code on GitHub. The one thing that is kind of sticking out now is when I head over to my events, we have in total we have 42 events. But I said, how many events should we have? 40. Another question is, this is one of the common things that kind of goes wrong. Any guesses why we have too many events? Well, let's figure out what we have in our data here. Let me open that one here, and let's extract, for example, the log level. If I click on that toggle the column, I can just show all the columns that I have in my data. And then I'll just have here the timestamp and that log level. And then when I scroll down, I see this one doesn't have a log level. When I open that one up and scroll down, you see, oh, we have a grok parse failure, and we have bad runtime. What is that? Yes, that is the stack trace. And that is basically the problem, that we collected the stack trace incorrectly. Because you see, the regular log lines, of which we have 40, that worked. But this one here, that is part of the stack trace, and we didn't collect that stack trace correctly. Or actually, we broke up the stack trace. Does one line of a stack trace make much sense? Not really, because a stack trace only makes sense in one unit. So basically what you will need to do is, when you collect that log file, you will need to define the right pattern. Luckily FileBeat can do that. And what we would need to do here is to say, like, every line starts with a square bracket, for example. If it doesn't start with a square bracket, then it's a stack trace. And then you should not break it up into a new line, but just keep it with the previous line. So basically say that these 3 lines here should be one message and not 3 independent events. That's the general idea of that. If you, for example, FileBeat, Logstash, if I see my configuration here, what you would need to do is you would need to enable this pattern where I basically say, like, yes, every line starts with a square bracket. If it doesn't, it's a continuation because it's a stack trace, and it shouldn't be broken up. If I would configure that correctly, then you would only get 40 events, and you would not have those broken up log lines. So we have seen we can simulate the grok debug patterns. That's helpful. The other thing that can be very helpful nowadays is Piotr showed you some machine learning that is in the commercial package. We have one component in the free package for machine learning that can basically try to detect what you have in a file. And we can also try that out hands-on. So if I had to the machine learning, this is the machine learning icon. I once was told, this doesn't look like a brain, but like a split brain, the one that you want to avoid in your cluster. And once you've seen that, you can never unsee that again. So for me, this will always be a split brain from now on. Anyway, so here I can now upload a file. So I'll take the log file that I have, and instead of actually parsing it, the grok pattern will say, like, oh, I think this might be a good pattern to actually parse that, and it can extract what you have in here. So if I make it slightly smaller, you can see it. You can see here, it for example, extracted the log level correctly. It sees that we have like a loop count, that's okay, we have a message, we have the session information, and we have the timestamp. So it's extracted that all correctly, and it gives you a starting regular expression. So basically you can build on top of that later on and don't have to write the regular expression all by hand yourself anymore. That should normally make your life much easier. And we also have a log UI. Let me quickly show you the log UI. It's basically, this is really like a tail F. This is just scrolling. Like if I add more events here, this will keep scrolling. And you could add live streaming. My application is not running, but it would just keep like tailing your files and show you what is happening here. So that is for the parsing part. The good thing is you can just reuse your log files. You don't have to do any changes to your applications. The downside is you need to write that stupid regular expression. Does anybody like writing regular expressions? I always called it the Stockholm Syndrome then. You just got so used to writing regular expressions that at some point you start liking it. Because I personally don't like writing regular expressions that much, but well, you can if you really like to. You need to be careful with timestamps, and multi-line messages are also kind of a bit of a pain. You can send data directly to Logstash, which would look like this. You have a special log appender that can talk to Logstash directly, and that would store the data directly in Elasticsearch, and you don't need to do any parsing. Any guesses what might be the downside of this? First, you have a bit more coupling between your applications, and second, what happens if your network is down? Depending on your log appender, like in Logback that I'm using, the buffer will be 200 megabytes. Once you reach 200 megabytes of unsubmitted logs, the oldest ones will be thrown away. So you might just not see what is happening in your log. What might be a more clever way to do that? The one we like is to actually structure your data. So instead of writing a regular log line, like this one here, you could just write it out in a structured format. We prefer JSON because Elasticsearch will take JSON as well. And if you have the right log appender, it can just write out the JSON directly. And the nice thing is, if you use that, you basically just tail the JSON file, and FileBeat can then store that in Elasticsearch directly, and then you don't need to do any parsing anymore. Because your log appender just knows what is what and can write that out correctly, and you can get rid of all the regular expressions and parsing. Configuration would look like this, but you will figure that out. That's pretty intuitive. There's a slight overhead for JSON serialization. Otherwise, this is what we would recommend and what will make your life the easiest if you need to do any parsing. Other than that, who is using a lot of Docker? Anybody heavy on Docker here? Okay, that's not that many. Anybody heavy on Kubernetes? Okay, because we type pretty well into those ecosystems as well. Just very quickly, since those were very few. Yeah, give me one, like, we'll wrap this up in 2 minutes. Just to say, if you're using Docker, we would generally recommend it as a sidecar, to run the FileBeat as a sidecar. And the architecture would then be, you can just tail the Docker standard output with the FileBeat and just forward those. And for Kubernetes, whether you put it for Kubernetes is ideally on a daemon set. We have a pre-configured configuration in the FileBeat repository for those as well. And it might then look something like this. We can extract the Kubernetes metadata, for example. We will know which pod, which node, which namespace. We can extract all of that from the Kubernetes metadata. We can also get data from the Docker metadata and forward those. So here we're doing something like this. And you could even customize the index. It's kind of very hot, but it also adds more complexity. But if you like Kubernetes, we do support that as well. I'll publish the slides afterwards. You can play around with all the code samples. It's very easy, and it's just minimal configurations. And these are basically your options to collect log files and work with them. Okay, we'll do questions later on. I'll just hand over to Piotr for the demo. Let me put together your fancy thing again.
Okay, so let's start with the other demo. So that will be a very extensive demo, which will cover full end-to-end analysis and operational analytics for application. So this application is actually e-commerce shop. So it contains multiple different components. So we have proxy servers in front of the application. Then we have Django-based application using Elasticsearch, MySQL. Then we have APM component, which enables us to look inside the application itself, how the all different calls to different components outside the applications are looking, how much time they take. And then we have that connected to Elasticsearch, Kibana Logstash, through bits as well, to get insight into all other parameters like logs and so on. So what you see here actually is email box, and on this email box we'll start from the first email, which is telling us about the high abandon rate. So what is abandon rate? So abandon rate is when you actually have shop, you have cart, you add something to the cart to buy, but finally you don't buy, you drop the cart. So abandon rate is when you don't complete the order, you don't complete all the process. So that's very worrying situation for e-commerce shop owners. When actually abandoned cart rate is going up, then that means that revenue is going down, so they are not selling, not earning money. So that's a very bad thing to have. So we get email. So machine learning is able to produce formatted text emails, that is mustache. So we can actually put here whatever we want. So we can automate tasks directly to those people who will be executing and finding problems. We can send these machine learning jobs automatically. So we click on machine learning job link, and then we'll be automatically directed to the dashboard, which will show us where anomalies happened. So this is our abandon rate analysis. So we see that we have two red squares, which are telling us that anomaly occurred here, and then our abandon rate is much higher. So what does it mean much higher in our case? So we see that the values don't differ too much, but they differ 10%. So in many other cases, 10% might be not much, but when we lose 10% of our income, that's quite a lot, right? So we would like to investigate more what happens here. So we can actually create in Elasticsearch different observations, different dashboards from financial investigation, application analysis, error impact analysis, and so on. So we'll start from business. So we'll see what happened to the business during this short period of time where we observe our anomaly. So those are the figures, business-oriented figures. So we see what kind of money was actually spent during this time. So we can see here how abandon rate is behaving. So we see growth, so average, and the abandon rate actually temporary values which are changing. Here we see that this is possibly correlated with the condensation, or actually more occurrences of errors. Here we have the errors, and we count the errors from the application. So like core dumps, other errors which are executed on the application. Here we can observe what will be the sales over time, so how much money we earn. And we can actually get far more observations to our data, so we can really get intelligence on how expensive this problem is to us. So we go back to our machine learning job, and now we can switch to application analysis. So application analysis is this APM part. So I don't know, any of you already used or heard about APM, or using any other APM? APM is application performance management. So it's like New Relic, other companies like this. Okay, so anyway, so if not many of you can see, know it, then I'll show what that is in our case. So we have here two different things. So we have response times on the left, and we have here requests per minute. So we can filter out particular responses. So we have 200 codes, we have 300, 400, and 500. So which codes are the most important from the operational perspective? Which codes you don't like to see? 500, exactly. So we don't see 500 that much, but when we filter out quickly, we can see that we have lots of them, right? So that's really bad. So we can quickly go to errors. And then Elastic is able to aggregate data and see what errors, how often these errors are occurring. So we can actually see which is unhandled exception. So let's go to that one. And this is called number pass exception. The string supplied did not seem to be a phone number. So we see here what is the distribution of these particular errors, how often they appear, and then we can see actually all the parameters on the application which are seen by the application itself. So we have a stack trace from the error, we have requests, so we see what actually was in the request. We have metadata related to this particular events coming, and this metadata consists of system information, service information, process information, so we can identify actually when this particular problem occurred. And then let's see how our stack trace looks. So we go to the bottom and we see here that we have a highlighted line. We can see that this actually causes number exception. We see what kind of data was supplied when this exception occurred. So we look at this phone number because this exception was telling us about the phone number. So we see that phone number is AAA. So we also see that this is the library which was actually called when this error occurred. So what's visible here that somebody forgot to put the exception handling syntax clause, so try catch, and that's why the exception was thrown and this particular error was unhandled exception. So let's go back to the initial observation. So we know that we can actually look at the errors. We can see what happens actually from the perspective of stack trace, but now let's focus on something else, performance. Because we all know that finding out why our application is not performant enough, we have queries and suddenly we don't have answers, or we wait like 20 seconds for answers, or maybe then it's even ended up by crash. So we can actually look inside that as well using APM. So here are the response times, different values. So we have average response times, not so interesting. Then this is 95th percentile and 99th. So we see that our responses vary from, let's say, few hundred milliseconds to almost 14 seconds. So who will wait 14 seconds for the website to answer? Probably no one from us. And that's why we really need to see what happened and why this application is responding so slow. So we can actually look here on particular different areas of our application, which endpoints are causing the most of the trouble. So here we have something which is called impact. Impact is calculated from the difference between average response time and then 95th percentile of the responses. And then also how many times per minute this particular requests were done. So we didn't see how impactful this problem is. So then we click on that and we see more analytics. So we see a distribution of responses times from our application. So we see that most of them are actually below 2 seconds, and there are even some which are reaching 16 and probably 17 seconds. So we'll pick one of them. So that will be 12 to 13 seconds. And then here we obviously see all this metadata related to our requests. And here we see interactions, different calls to different systems. So those are SQL queries. And we have some REST calls. And then we see that one of these calls, actually one of the queries to database, is taking more than 10 seconds. So I will click and I will try to identify what happened here. So I see the code responsible for this particular call. So I know where this is queried. And then let's see how the data and related calls are looking in our database. Let's try to identify which exactly element of our website is involved in this problem. So I have already pre-highlighted interesting columns from our data set. So that will be obviously date, the component which is correlated with this particular event, span type, so this is a code tagging basically, and then we have Elasticsearch logs. So we will follow this query, so we can add embedded links to records, so those will be URL fields. We can add also some scripted fields, which will be transforming, but this is actually the link to other data set related to this particular events, so that will be different logs. And now we see how this Elasticsearch log related to this SQL query was looking like. So we see that query size is pretty big, number of hits is also big, so we are reaching limits here, so very long time to respond. And then here we have source URL. So this is the URL used by a client to retrieve this particular component. When we click on that, we will wait exactly 14 seconds. Actually 14, 13 seconds, exactly what's in our APM to get the content, and in a few seconds, when the process will start, all these queries, responses will be done, you will see SOCs. And this is how we could actually reproduce problem reported by your customer by looking into our APM data and quickly get to the point what we need to fix. Actually, the queries were wrongly written, so they returned too many results. Obviously, it was very heavy, and that's why the whole process took a long time. So from that perspective, we understand where is one problem, but then we possibly have more problems. So I will move back to machine learning jobs, and then we'll look into the infrastructure analysis. So again, we have machine learning job, which is telling us that our application, actually whole system, is not performing fast enough. So we have this red line here that we see that most of the components are affected here. And we would like to see what happened in this particular period of time. So machine learning identifies really longer responses, so really bad behavior from our application. That's fully automated with machine learning job. And then we will follow the link again. So we see 20% longer responses. And then we go to infrastructure analysis. So Philip was already telling a little bit about ingesting different data to the cluster. So this is how you can achieve it in the real-world solution. So we have combined views on multiple different components. So we have data from APM. So this is how the responses are measured. So we have memory usage, we have CPU load, and look at that this is across all components from our system. So it's not only one machine, but all the machines. Disk I/O, those are rare events based on significant aggregations. So whenever something is uncommonly common, we call it uncommonly common, so which is related to particular events, and those things are visible, but not very common across everything else, and those will be marked here. So it's like a noise removed, and we have those only important, which are not occurring so often. Then here we have similar thing, that we have all processes from audit bit. We have networking connections, heat map of networking connections between components, data throughput, database queries, and the process executions on the nodes. So what we would like to understand is why this rise in the response time happened, so we can quickly filter out by this particular period of time. Then we can follow up things which are really looking unusual. So when we look at things, we probably will focus on the spikes here, and we would like to see why our CPU is much higher. So we go here, we filter that a little bit more, and then what we see by clicking that something strange happened on the heat map. That probably you don't see that very well, but there is MySQL and proxy. And how often proxies are talking to MySQL database? Not very often. So it's probably a good idea to investigate more what happens in this connection, actually what happens on these two components. So we can create filters, and I will apply filters to the proxy server. So I will review other things, and then what I notice here, that something appeared on my significant term aggregation, so rare processes which are running, and I see reported POI. So when I click on this reported POI, I suddenly see that this reported PY is executed periodically, and it may have impact on my performance. So I'll change the observation period, I'll actually disable this filtering, and then suddenly I see that this is correlated, this process when it's executing is producing this kind of CPU load on our system. So this is actually to show you that you can go from looking at the performance CPU load to identify strange things running on your system, and this is actually fully automated. It's pointed by machine learning which period of time is actually the problematic periods of time. Because if you think about systems which you may run, then you don't know actually when things are happening, usually, because you don't watch this 24/7. And even if you watch, then probably you will not notice all the details. So this is the part related to like whole infrastructure monitoring. I can show you also, I don't know. Oh, sorry, we have 10 more minutes. So I will show you the application of Kubernetes. This is the small application deployed, and then you'll see how Kubernetes application can be deployed. This is a little bit small here, but I will just follow up on what Philippe said about the sidecar. So can you tell me how many of you know what a sidecar is? Okay, so at least a few people. So then I will quickly maybe go through the deployment files. So what is a sidecar? Sidecar is actually when you deploy application in Kubernetes, you create so-called pods. Pods will contain containers, Docker containers in most cases, because Docker is very popular across Kubernetes. However, this is not limited to Docker only. And then what happens when you have applications? Application may be shipped by developers, it may be packaged to a Docker container, and how to get logs from this kind of application. So usually applications will push all the files, all the logs to central place, to standard I/O. But then what happens when you actually like to monitor more than one file? Then you would like to, you will need to create something else than standard I/O. You will need to create sidecar. Sidecar is another container which is tailing log from the shared file system. Shared file system is actually attached to the original container where the logs are written. You can have many of them. And then sidecar is actually also mounting the same file system. So then the standard tail command, like we have here, can be used for tailing this out, and then basically you can deliver these logs to file. And then how we can configure file bit and metric bit. So file bit and metric bit was very important from operator perspective, that they are only installed once as a daemon set. So they have auto discovery function, so we can describe the rules which tells us which containers in the pods, or which pods should be monitored. So metric bit is metric and file bit are subscribing to a Kubernetes engine. It can read events. They can see data in etcd. So basically, whenever new components are created, new pods are created, those data is getting to the file bit and metric bit, and those are getting monitored. So as Philip mentioned, so we can download daemon set configurations, so only the rules will need to be created, and obviously applications will need to have these sidecars created. So it's not very complicated. You define volume, it's like this, then sidecar few lines, and then you have just regular deployment for your application. And then how the monitoring of Elastic of application looks like. So let me quickly go to Okay, so just quickly, few words. What was the application? So application is a honeypot. This honeypot contains 3 components, 3 different honeypots dedicated for different observations. So one honeypot is observing logins trials to our service. So this is deployed in a standard way on the internet, so anybody can connect, and then we see what happens. So I will show you first how honeypot data looks. So we are getting connections from many places in the world. So this is part of these 2 visualizations are pretty new to Kibana. Those are based on Vega. Vega is another language to create more fancy things. So this is going beyond what's possible in Kibana itself. So you can define all views, even 3-dimensional, as you can see here. So you can create rotation globes. You can create Sankey diagrams, which are showing the flows between particular components. So we have here on the left and the right side, we see different honeypots, and we see how users are connecting to both and links between those 2. Then Kubernetes and what we see from the containers perspective. So we have multiple different views. So we have containers overview. So we have all the data like CPU load, memory usage, and so on. Then we can see all the most important stats from nodes from the system as a system overview. And then we have host overview and containers overview. So those will be stats. Just a second. Okay, so for some reason it works a little bit slow, but okay. So this one actually is going slow. Okay, so this is the view for Kubernetes itself. So Kubernetes will be identified, so we'll see how many deployments are desired, how many of them are available, how many unavailable. So here this line is actually describing each particular pod. When it's available, then we have one more line here. And then all the stats from particular Kubernetes pods and then nodes. Then we have something which we developed pretty recently. So that's from version, I think, 6.4. Infrastructure monitoring. So this will visualize, actually look on your platform. So we'll have summary for nodes. When you have more nodes, you'll see these nodes. Every single node can be, you can look inside the components. I'll just show you maybe on Kubernetes. So we can look on, so those are all pods which are deployed on my deployment. And I can look at that through different perspectives, from CPU, memory, inbound traffic, outbound traffic, and so on. So it will put the colors on particular components, and I can review what happens in the metrics actually on this particular component. So this will provide you a summary for all the things from the system. So this is in short what's possible currently in Elastic from the logging and observation perspective. So I don't know, possibly we'll switch to questions and answers now, because that's all from demos. I don't know, Kenny, if you want to add something on the end of the conversation. So yes, so I think that will be good. Probably you have some questions. Yeah.
What we can do, guys, is that you can ask up to you and ask questions. We can go up to you directly and ask questions after this now. Is that okay? Okay, so I'd just like to thank everybody for coming, guys. I hope the event was informative. You've learned quite a lot from it. A special thank you to Elastic for coming tonight. Thank you to the speakers with Paul, Piotr, Philip, and Richard from Data Practitioners. So put my hands together for you guys. Thank you. We're going to post, we'll share all these slides with you guys. We'll post up the video as well for any, so you can see all the information. Like I said before, we're building an ecosystem here around Elastic. We need your input. We want to build a community. So any feedback, please do share with us on our website. And let's go from there. And a big thank you to my team, because massive amount of work that goes into organise these events. So the tech team, we had Matthias, and we had Rafa. Thank you guys. We had from the girls organised. We had Annetta, Monica, Ola. We had Guccio, and finally a huge thank you to Kasha. Where's Kasha? Kasha, who's is the key person tonight. She's organised everything and has been leading the event and manages all the events for us. So thank you so much, Kasha. She's in hiding somewhere at the moment, but she'll be back in a moment. So thank you for coming, guys. There's drinks, please. Feel free to join us for a couple of drinks, some food. We're going to stay around for a while, and hope to see you again soon. Thank you.